All right, so in this chapter, we've talked about a couple of different topics. One was Lewis structures, so predicting the layout of atoms within a molecule. And then in the previous video, we talked about molecular shape. Today, what I want to do is kind of switch gears a little bit and talk a little bit about electronegativity. And it's kind of weird to think of it this way, but some atoms are greedy. So some atoms are greedy and they hog electrons. So greedy isn't the scientific term, but I feel like it's a pretty good term to explain it. So some atoms just don't like to share, and that's a good way of describing electronegativity. So this is called electronegativity. Not all atoms are like this, it's only some of them. So then the question is, well, which atoms are greedy and which atoms aren't greedy? So I've got a good chart because this has actually been measured. So let's pull up this chart, and this is one I just got off of Wikipedia. You can find it in most textbooks, but this is called the Pauling scale. It's based off of a famous chemist named Linus Pauling. He's from Oregon, and he actually won 2 Nobel Prizes, one in chemistry, and then he won a Nobel Peace Prize, but that's neither here nor there. And you can see this electronegativity table. And one thing I really wanted to point out was it's actually pretty easy to predict because he said that as atomic radius decreases, ionization energy increases. So those were 2 trends that we covered already. But this follows the same trend as electronegativity. So another way of thinking about this is electronegativity increases as we go to the right, and it increases as we go up. So it's a pretty easy trend to remember because it follows a lot of the previous trends that we looked at. So if you look at the periodic table, you could say, well, what's the greediest element of them all? Well, it looks to me like fluorine would be. If you look in your book, it's listed at 4, 3.98 just has more sig figs, so it's definitely going to be the greediest. The other thing I would say is just ignore these right here. Normally, we don't consider noble gases greedy. They are a little bit, but that gets way beyond what this class covers. So fluorine is really greedy. It wants to hog electrons. So let's go through a few examples with fluorine. So let's consider elemental fluorine, which is just F2. This is fluorine gas, right? So we know fluorine is really greedy. Let's first draw the Lewis structure. So we've got 2 fluorine atoms, and I'll just draw them out like this. And fluorine is in group 7A, which means it has 7 electrons in its valence shell. Okay, and then we could do the same thing over here. So we could imagine this bonding together via a single bond. That way each of them has a full octet of electrons, right? So this is what the molecule fluorine would look like, right? Nice simple molecule to draw out. Okay, so the question is, both fluorines are greedy. Meaning they want to hog these electrons that are being shared between them, right? So the question is, what happens? Well, I like to think of this as kind of a tug of war, right? So they're greedy, they want to pull the electrons closer towards them. So if you have 2 fluorines, I would say that there's going to be a tie in this tug of war. So there will be a tie in the tug of war. Basically, it's just saying they're evenly matched, neither side will win, and there's no winners, there's no losers, they're just kind of unhappy, and that's the status quo. This type of bond is called a nonpolar covalent bond. So let's go ahead and define that down below. So if there is a tie, the bond is called a nonpolar covalent bond. So this is a term we're going to use a lot throughout this course. It's really important to remember that it's nonpolar if there's just a tie overall, and we'll talk more about how shape actually factors into this in a little bit. But let's consider another one. Let's consider HF. This is hydrofluoric acid. If you ever watched Breaking Bad, this was the nasty stuff that they tried to dissolve a body in. It's not something you want to mess around with. It'll actually etch your bones a little bit. It won't actually dissolve a body. That was just Hollywood. All right, so we've got hydrogen and we've got fluorine. Hydrogen has 1 valence electron because it's in group 1A. Fluorine has 7. Like we said, it's in group 7A. And if we think about the Lewis structure for this, it would have a single bond between these two atoms, right? So in this case, we could go up and we could look at hydrogen on the table, and hydrogen is over here. It's got a value of 2.2 versus fluorine over here. That's 3.98. There's definitely going to be a winner here, right? Fluorine has a much larger electronegativity value, therefore it's going to win this tug of war. So let's go back down and show how we show the winners and losers here. So the way we typically show this is with what's called a dipole arrow. And what this means is this arrow shows the pole of electrons, right? So the fact that it's an arrow going to fluorine means that the fluorine's pulling electrons towards itself. All right, there's another way of doing this too. Occasionally you see it where you show it with delta symbols. So delta negative means that the fluorine, because it's hogging the electrons from this bond right here, has an excess of electrons, right? Meaning it's got more negative character to it. So we'd show that with the delta negative. And then on the other side, because the hydrogen's getting its electron density pulled away from it, we could show a delta positive. So delta negative means electron rich. Delta positive, it means electron poor. It's getting the electrons kind of pulled away from it. So we'll see this used a fair amount. Okay, so now we're running into a situation where fluorine is clearly winning this tug of war. So let's talk about this. So we're now looking at this bond right here. So if there is no tie, the bond is polarized, meaning it's not shared evenly. This is called a polar covalent bond. Okay, so pretty straightforward. If there's a tie, it's nonpolar covalent bonds, or if it's a tie, it's called nonpolar covalent bonds, and if there isn't a tie, it's called polar covalent bonds. So not too bad. So let's kind of summarize this. And what this delta symbol means is the difference. So if we go back up to this table and we subtract these two values, we're looking at the difference, right? Which would be a delta. So if the difference in electronegativity between two atoms is 0, then this is called a non-polar covalent bond. All right, what about if the electronegativity is between 0, sorry, this should be between. What if it's between 0 and 2? Well, it's not 0 anymore, so I would call this a polar covalent bond. But let's go back up and consider, well, what happens if you have a difference in electronegativity greater than 2? So let's see if we can find an example situation on the chart with two atoms where the difference is greater than 2. So I'm going to now use, I don't know, my green highlighter here. And I'm just going to pick on my favorites. I'm going to pick on sodium over here, so 0.93. And I'm going to pick on chlorine right here. Whoa, that's a terrible color. So chlorine would be right here. That would be 3.16. Well, if we subtract those two, right, it's going to be a value greater than 2. So if we think about, well, what happens when we combine sodium and chlorine? Well, that's sodium chloride. That was one of the compounds we talked a lot where it forms an ionic bond. So if the difference is greater than 2, we're no longer dealing with electron sharing. In fact, the chlorine is so greedy relative to the sodium that it's just going to steal the electrons, and instead you'll have a cation and an anion. So this would be called an ionic bond. All right, so this is kind of going to be our guiding principles as we look at individual bonds. But now let's kind of take a step back and look not just at bonds, but at entire molecules. So molecules can have polarity too. So this time, rather than looking at individual bonds, we're going to look at entire molecules, the entire thing. So let's just make a note, not just bonds. However, we need to do a bit more work for these. But it depends. Sorry, that's messy. On shape. Not just the difference in electronegativity. All right. This is also known as, so I'll just say AKA, because these are used interchangeably a lot, a net dipole. And the way I always remember net dipole is I just say it's the sum of all poles. Right? So we could have bonds where there's a pole going on, but the net dipole is looking at the sum of every single bond within a molecule. So let's do an example. And I'm going to pick two different molecules. I'm going to pick NF3, that's nitrogen trifluoride. We'll talk about how to name these later. And then over here, we're going to do BF3, so that's boron trifluoride. And let's first do the Lewis structure. Before we do anything else, let's do the Lewis structure. And if I do the Lewis structure for these, I would want to count up the number of valence electrons. So I'd say, all right, if we think about nitrogen, nitrogen has 5 valence electrons, right? Because nitrogen's in group 5A. So I'd say, well, the nitrogen's going to give me 5. And then for fluorine, I know I've got 3 of them. And each fluorine has 7 valence electrons because it's in group 7A. So that's going to be what? 21 plus 5. It's going to give us 26 electrons. All right, so let's go ahead and do this. I've got nitrogen. I'm going to just stagger out my fluorines. We know that there must be a bonding pair between each of them. So we'll go ahead and do that. And now let's fill in the remaining electrons. So if we think about it, we've got 20 electrons left we've got to fill in. So let's just go ahead and try. So we'll count up to 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, it looks like everything has an octet now. So we can go ahead and say, well, this to me looks like it would be this Lewis structure. And we'll go ahead and put in all our dots in here. And voila. However, we need to think about the overall shape, right? Because we said that this isn't exactly right. It's not going to be 90 degrees away from one another. If we think about this central nitrogen, it's got a lone pair and 3 bonded atoms around it. So 4 things around that central nitrogen. It would want to orient itself into a tetrahedron. So let's go ahead and kind of redraw this using a little bit different form. Sorry, I'm going to zoom out so I have more room. And I would go ahead and I'd say, Well, we're going to have kind of three legs sticking down. So I'll do one of my fluorines like this. I'll do a wedge. This kind of means that one fluorine is sticking out towards us. And then I'll do a dash back here. And then the lone pair is going to occupy space right there. In fact, let me keep those as black dots. But the benefit of doing this, right, is this gives us the 109.5 degree bond angle. So this is a tetrahedral electronic geometry. And if we want to describe the molecular geometry, meaning the overall shape of just the atoms, ignoring the lone pairs, then we would say that this is trigonal pyramidal, because it's like a little pyramid where the nitrogen's the top of the pyramid and the fluorines are the base. All right, so we've got this structure done. Let's do the same thing with boron. So we've got a valence for boron that's just 3. It's in group 3A. And we've got 3 fluorines. We said they're in 7A, so we're going to do 3 times 7. So this is going to be 21 plus 3. This is going to be 24. So really, this is going to look remarkably similar. But there's going to be a subtle difference. So we've got 3 fluorines. We know we have to have bonding pairs between them. So I'll go ahead and fill those in. So we've got 2, 4, 6. We've got 18 electrons left to fill in. So let's go ahead and do that. So I'll count to 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right. And boron is this weird element where boron doesn't need a full octet. So in this case, boron's actually happy without an octet. So I'm just going to make a note here. So note, boron doesn't need an octet. Okay, so let's draw this. So now we've got boron bonded to fluorine. Let me draw this a little bit better. We've got 3 fluorines bonded to boron like this. Sorry, my cat's doing this crazy chase around me right now. She's got a lot of energy. But either way, here we go. We've got boron trifluoride. And then over here, you notice the only difference between these is nitrogen has a lone pair and there's no lone pair on boron. So let's look at the 3-dimensional shape for boron if it only has 3 bonded atoms and no lone pairs. Well, in this case, we don't need to think about 3 dimensions as much. Instead, it's just going to kind of stagger out into a triangle. And I'm just going to leave, or actually, let's do the lone pairs here, just to be super thorough. And let's include the lone pairs on this one too. All right, and by doing this, we're going to maximize the bond angles and we're going to make them 120 degrees. All right, so we've kind of got the back work done on this, but now we need to look at bond polarity, right? So I'm just going to erase these bond angles for now to kind of keep things clear. We know that fluorine is the greediest of all elements. So fluorine is going to hog from this nitrogen in all of these directions on that molecule. And then same thing over here. I'm not going to do the delta symbols because we've already used the arrows. This should be good enough. Okay, so we've got individual bond dipoles where fluorine is hogging electrons away from the adjacent atom. However, let's think about the sum of the poles. And let's think about over here with boron. I would say that really because of symmetry, the poles will cancel. Therefore, this molecule, if we look at it, is nonpolar, and there is no net dipole. So even though there's individual bond dipoles, there's no net dipole. Therefore, this bond is going to be nonpolar because there is no net dipole. Okay, let's think about the other one though. Well, in this one, we're dealing with a different situation. Each of the fluorines is kind of pointed down underneath the nitrogen. So if we add them up, the net pole is going to be directly underneath the nitrogen. So I could show that using another bigger arrow. So in this case, the net pole is down. Therefore, this molecule is polar and has a net dipole. So like I said, we can't just immediately look at the formula. We have to take into account the shape. A lot of times students will look at problems like this and they'll say, well, NF3, BF3, they look the same to me. We're just swapping a nitrogen for a boron, but it's this pesky lone pair that changes absolutely everything about the shape for the nitrogen compound. So we have to consider the overall molecular shape before we jump into deciding if a molecule is going to be polar or not. All right, I hope that helps, but let me know if you have any questions.